Now, we were looking at microcanonical ensemble. And this is corresponded to an isolated system, the language of thermodynamics. And here the idea was to determine rho of xn, or the probability density rho of E is equal to 1 over E comma x, right? This essentially, we have seen that this is the total number of microstates. Microstates for a given energy E, right? So this is what one must keep in mind. In doing calculations with microcanonical ensemble, one should always calculate for the total number of microstates for a given energy E. Now, whatever all the derivations and all the calculations that we did in the earlier class, we had considered the system where my phase space variable, the microstates, could take continuous values, right? Because for example, the system that we were particularly interested in was an n-particle system, which is similar to like a gas or a fluid contained within a box, and there was an associated Hamiltonian for this system, right? And this quantity, the state, could take real values on the phase space determined by the conservation of the energy. But it is also, this is not the only type of systems that we'll encounter. For example, this is clearly the case when we consider an ideal gas, right? But there are systems where the states are discrete. For example, one can imagine a spin system on a lattice where the spins can take up or down, up and down value. Here, the microstates are clearly the states, the configuration of the spins, right? We will do that a little later, but the idea that I want to impress upon you is that there are two possibilities one needs to look at. One, where your microstates can take continuous values as a random variable. Here, for example, this xn is a random variable, and in the other case, where your microstates can take discrete values. So we'll start off with a very simple system in what is known as a two-level system. This two-level system has two energy states. Let's call them 0 and let's call them epsilon, right? Now I put in n particles in this two-level system. Some of them are clearly going to occupy the 0th level, so we will call them n2, and some of them is going to occupy the first excited level. We'll call them n1, so that n1 plus n2 is equal to n. Here the microstate is defined by the occupation number. So first particle zeros, second particle can be epsilon, which we denote by 1, 1, 0, so on and so forth. So the occupation number ni will define the microstate of the system, so that the total energy we can write down as sum over epsilon I ni, which becomes n1 over epsilon. For all those particles which are occupying the first level, excited level, for all those particles which occupy the first excited level contribute to the energy, the ground state does not contribute to the energy. So we have therefore n1 as E over epsilon. Now I want to find out the total energy, total number of microstates. So this is the case where my microstates are discrete, and I want to find out the total number of microstates omega corresponding to this. So clearly this is a problem in combinatorics. I have n1 factorial, n2 factorial, and I have ni epsilon I, right? Sum over I. This would be n factorial. This guarantees, this delta function guarantees that this is obeyed. So therefore this becomes n1 factorial, n minus n1 factorial, right? So ln of omega e is ln n factorial minus ln n1 factorial minus ln n minus n1 factorial, which if I use the Starling's approximation, this becomes n ln n minus n minus n1 ln n1 plus n1 minus n minus n1 ln n minus n1 plus n minus n1. Let's simplify this. You clearly see that this n1 is going to cancel with this plus n is going to cancel with this. You are left out with n ln n minus n1 ln n1 minus n minus n1 ln So we have this expression. Now let's simplify this expression. I want to add ln n minus n1 ln n plus n1 ln n minus n1 ln n1 minus n minus n1 ln of n minus n1, right? So then let's combine this one with this one. So then I have minus n1 ln of n1 over n. And if I combine these two, I have plus n minus n1 ln of n minus n minus n1 ln of n minus n1, which is minus n1 ln of n1 over n minus n minus n1 ln of n minus n1 divided by n. So this reduces to the very simple expression n1 ln n1 over n. There has to be an n outside here. I can recall. Now this is fine. n1 ln n1 over n minus n minus n1 ln 1 minus n1 over n. If I take n outside minus n, then this becomes n1 over n ln n1 over n plus 1 minus n1 over n ln 1 minus n1 over n. Therefore, the entropy, which is a function of e comma n, is ln omega e comma n with a kb sitting outside is minus nkb n1 over n n1 over n plus 1 minus n1 over n ln 1 minus n1 over n. But n1 is e over epsilon. So n1 over n is e over n epsilon, and therefore I have nkb e over n epsilon ln e over n epsilon plus 1 minus e over n epsilon ln 1 minus e over n epsilon. And this gives me the entropy as a function of e comma n. Recall, from thermodynamics, this relation is what we call as fundamental relation of type 1. And there we said that within the scope of thermodynamics, it is not possible to derive this equation or these relations. But given these relations, you can exactly derive all the properties of the thermodynamic system. But now here, from the microscopic picture, we have very nicely derived this fundamental relation of type 1. So how do we proceed? Well, we proceed by looking at this. This is 1 over T. I know the derivative is going to be inverse of temperature. So if we calculate the derivative, del S del E is going to be minus NKB 1 over N epsilon ln E over N epsilon plus E over N epsilon 1 over E plus, this is going to be a minus 1 over N epsilon ln 1 minus E over N epsilon plus 1 minus E over N epsilon times 1 by 1 minus E over N epsilon minus 1 over N epsilon. Now this is a lot of simple algebra that one has to do, but that is nothing very difficult and is absolutely doable. The left hand side is 1 over T. So that means I have 1 over N epsilon ln E over N epsilon minus 1 over N epsilon ln 1 minus E over N epsilon plus 1 over N epsilon, and this is going to be minus 1 over N epsilon. So I have 1 over NKBT with a minus sign is 1 over N epsilon ln E divided by N epsilon 1 minus E over N epsilon, right? So therefore, if you take the N epsilon to this side, you have ln E over N epsilon 1 minus E over N epsilon is equal to minus E over KBT. So that E over N epsilon 1 minus E over N epsilon is equal to E to the power minus E over KBT. Good. So now one proceeds to simplify this expression. So I can write down N epsilon minus E to the power minus KBT. So that E, if I bring it to this side, 1 plus E to the power minus E over KBT is equal to N epsilon E to the power E over KBT. Therefore, the energy as a function of temperature becomes N epsilon E to the power mu over KBT divided by 1 plus E over KBT. Right? Now the question is, okay, whether we are correct in all our calculations. Let's see. So let's take the limit of T to 0. If I take the limit of T to 0, then 1 over KBT tends to infinity, right? And the total energy would tend to zero. Correct? Why? Because as you lower and lower the temperature, there is not much of an excited energy available to go to the first excited level. So correspondingly, all the particles are in the ground state. What happens to T to infinity? T to infinity would mean that KBT goes to 0, and you see E of T goes as N by 2 epsilon. So you have so much of energy available that half of the particles populate the first excited level, half of them populate the ground level, so that the total energy is n by 2 epsilon. From this, of course, given E of t, one can calculate the specific heat as a function of temperature, which is del E del T and constant. This I leave it as an exercise.